Hello, everyone. Now that we're finished with the quiz on waves and oscillations, it's time to move on to our next topic, which is sound. And sound is going to have a lot of similarities from what we've already worked at with waves. But since this is the introduction for it, there are a couple of ideas that are different. I wanted to do this recording to explain through some of the concepts. And so I probably won't be doing a recording every day, but we just have it for now. This will help me a lot to work through the PowerPoint, show some pictures, and then do a couple demos to compare sound waves with what we've already seen in the last chapter on oscillations and waves. So, as you probably already know, sound waves are a type of longitudinal wave, specifically a longitudinal wave in the air. And it's caused by when you're speaking, or you could also be done by hitting a drum, plucking a string, but you're causing air molecules to oscillate back and forth. And where there is a greater amount of air, like a compressed air, you're going to have a compression point. And then the opposite of that will be a rarefaction. And so just like we could measure wavelength by measuring distance from crest to crest or from trough to trough, the equivalent with sound waves is that you would measure from a compression point to a compression point. And so that will be your analogy for a wave. As far as pressure wave goes, I like this little graph here. So you can see that where in the pipe you have a bunch of compressed air, lots of air molecules close to each other, you're going to have a higher pressure just because there's more things in a small area. Where you have the rarefaction, you'll have a lower pressure. So it's causing it to be above or below that equilibrium point. Whereas on both ends of the pipe, it's just going to be the same pressure as the rest of the atmosphere. So that's why at zero and at the very end, we have pressure that's at equilibrium at zero, and then it will go up when it gets to compression and down when it has a rarefaction. And this is specific to standing waves that we'll see in pipes. Of course, there are other ways of creating sound. You don't always have air traveling through a pipe. Especially a good example would be when you have like a string that you're plucking. It's not going to be traveling through a pipe, but through a string. But this is probably the biggest difference that we have, and that's why I want to go over it. So sound waves that'll travel from an open tube, from one end to the other, they're going to be having atmospheric pressure on both sides. That would be, as it's transmitting from one form to the other, you're going to have that sort of wave depiction based on the amount of pressure at a given point. I wouldn't worry too much about having to graph this yourself. We're going to try and stick away from using like mathematical formulas or other big calculations with this unit and stick more to the real life applications. But understanding why different pipes or different types of tubes create different sounds, it is important to be able to see the graph and understand how pressure is going to be different at different points. So just to read through the slide, make sure that everything is making sense. Sound waves traveling in a tube will eventually reach the end where they encounter atmospheric pressure of the surrounding environment. So that is, again, why we're just saying that the atmospheric pressure is going to be zero or equilibrium point. So as long as we have two open ends, we're always going to have pressure being zero at those points. And then the wave's energy is transmitting into and out of the environment. And that energy, you have some energy that is kinetic energy because you have particles that are moving, but some of it is also being transmitted as sound. And yes, once again, we have air sloshing back and forth that's causing the pressure. And the first type, the type that we've mentioned already, will be an air column that has both ends that are open. And I have an example here. That would be a straw. So both sides are open, and when you blow air through it, it's going to create a standing wave, kind of like if we picked the right frequency and the standing waves lab on a string, we'd get really nice standing waves. So depending on the length, air is going to find that perfect standing pattern, and that's why depending on the length of something you have, you'd end up getting a different pitch. So if I blow into this, you hear a note out. And similarly to when we talked before about like speed of waves, And that is entirely dependent on the medium. So I can't change the pitch by blowing harder or softer. That is only going to affect the amplitude or the volume. But everything has a resonant pitch or a natural pitch or frequency that it's going to have. And that is just depending on the length, or it can also depend on the density. Example, air has a pretty typical density, but if you think about helium versus normal air, one is going to be more dense than the other. And so that would be the reason why when you breathe in helium, your voice ends up sounding higher because your voice is traveling through a different medium. It's going to be traveling at a different speed. And you end up hearing your voice sounding higher. So that's kind of a cool example. Unfortunately, I don't have any helium balloons in the house to demonstrate this. Probably not a great idea. Breathing in too much helium isn't great for you either, but it is a pretty cool example of how the properties of the medium are going to impact the type of wave that we see, either in physical, like mechanical waves, or in sound waves, which we can't see, but we can still hear the examples. So moving on, air molecules can be in a tube that's open on both ends, or you can also have a closed end. And that is going to create a different pattern. So but when we had both ends that were open, we always had those nodes on both sides because it was at atmospheric pressure, so basically at zero. We're going to see a difference when you have a closed end, and instead you'll have an antinode. And we have a couple nice depictions to be able to show that coming up. So once again, here's the graph with open tubes, and we have nodes on both ends because on both ends there's atmospheric pressure. And the most simple of this, we have the number of modes. So just like you have the first harmonic when you have a single standing wave, that would be the first mode here. When you have the second, then you'll have two antinodes or one full wave. Three would be three antinodes or 1.5 waves. And you would be able to calculate the wavelength using this picture in the exact same way that we were doing it with our lab that you used for the quiz. And the most simple one in the second harmonic, when you have one full wave, the wavelength would be exactly the same as the length of the tube itself. The difference comes in when we have one end that is closed. So when we have a closed end, the end that's closed doesn't have atmospheric pressure. That one is going to be constantly fluctuating depending on the air that you're blowing in. So instead of having a node at that end, you're going to have an antinode. So that means that the simplest version, the first harmonic in a one end open, one end closed system, that's going to only be 1/4 of a wave instead of half of a wave. So if we wanted to find the entire wavelength in mode 1, we'd actually have to multiply it by 4. Whereas mode 3, you see that we don't ever have a complete antinode, or there's always one incomplete antinode. And that's because we're never going to be able to have a node at the end that is closed. So for this third one that we have 3/4 of a wave. And you can see that if the length is identical in these, so I have an identical open, and I have, all I have to do is close the end, but the length stays the same. If we're just considering that very first harmonic, this would be, when it's open, half of a wave. So let's say this is about 10 inches. Total wave would be 20 inches. However, if I close one end, all of a sudden my first mode is going to be only 1/4 of a wave. So if this is 10, the entire wave would be 40 inches instead of 20. So we have a wavelength that is twice as long when you close the end. And that ends up changing the frequency that you'll hear. Because if velocity is equal to frequency times the wavelength, and the velocity is staying the same because I'm not changing this density, I'm not changing the density of the air, I'm not changing anything that I'm blowing through. For the wavelength to increase, the frequency has to decrease. So if I blow in with it both ends open, and I now close one end, I should expect that because the frequency is decreasing, I'm going to hear a lower note. So that will depend on, that will actually change the note that you hear, which I think is pretty cool. However, again, the note that it is entirely dependent on what I'm blowing into. So I can change it by having it open and closed. I can also change it not so easily with a straw. This is a reusable straw. I don't have any plastic straws in my house, so I can't cut this to demonstrate, but I do have an example with a glass. Oops. So this doesn't have so much to do with standing wave sound waves, but I just want to drive home the idea of changing the note or the frequency by changing the medium. So if I hit this, it's going to have that note, and that should be it shouldn't matter how I hit it. I can get that note either by hitting it, or you can also sometimes do rub it around, and it sounds different in the quality of the note, but the note itself is actually the same as whether you hit it or if you do this fun technique. So one way I can change the pitch that we're hearing is by pouring some water into it, and then the length that air has to vibrate back and forth has changed. So we now have a shorter length. Let's see what that does to the pitch. So it ends up getting lower in this case. And that has to do with like, the density of the sound is traveling through. But we can also relate this whole idea to different types of instruments. I won't get into that now, but hopefully you can understand the difference between an open and a closed tube from this as far as how the standing waves are going to look. Once again, the open is going to have a note on both ends because both sides have atmospheric pressure. The one side open, one side closed is going to have a note on one end and then an antinode on the side that's closed because that one won't be at atmospheric pressure. That will impact the wavelength and thus the frequency that we end up getting out. So hopefully this makes sense. All that you need to do for today as far as an assignment is to go ahead and submit a sentence, a question. So either a question that you still have after this video, something new that you learned, or a comment relating what you see here to everyday life. So that's all for today. Hope this was helpful, and I guess I'll see you back tomorrow.